Hello again, Galen Pickett, Cal State University Long Beach. This is Physics 151, and today I want to talk about Section 5, Chapter 9, Analyzing Point Particle and Real Systems. So, what I have here, what we have is 9.5, is a system that we're gonna analyze. I've got a puck. You're looking face down on a puck that's sitting on a frictionless surface, and I'm going to put a force on the edge of that puck, and that force is pointing upwards, and I'm going to let that force act for a time delta t, so the object, the center of the object, goes a distance L. So I've got an initial and a final states. So one thing I want to know is, what is the final velocity? This disk has a moment of inertia moment of inertia I and a mass of m. So the point system, I consider the entire system as a point. All the mass is concentrated at the center of mass. And all of the forces, the net force from the surroundings, acts at that point. So I can't tell that this force is being applied at the edge. What I would see for the point system is something that looks like a mass m. It's got a force F on it, and after a time delta t, it's sitting here a distance L away with a velocity v final. So I could tell you what the v final is, the energy principle, the change in the energy of the system, and now since it's the point system, it's really just the translational energy, is equal to the work from the surroundings, the net work from the surroundings acting on the center of mass. So what I've got here is the translational energy of the system. The final state is 1/2 m v final squared minus 0 because it starts at rest, and that is equal to F times L. So the final is square root 2FL divided by m. And that, very simple to find. So I know how fast this thing is going. And yet, this thing does have some spin to it in the final state. So for the point particle system, I know that this is the translational energy. What is the rotational energy? Well, if I knew what the omega final was, E internal, which in this case would be just E rotational, would be 1/2 I omega final squared. So I've got these competing ideas. I've got the total change of the energy of the system for the real system is equal to, I've got my final kinetic energy, 1/2 m v final squared. I've got my final rotational energy plus 1/2 I omega final squared, and that is equal to the work from the surroundings, which, let's suppose it's just F times L. I've got this object has moved a distance L, and there's a force F on it. Well, we know from this analysis that 1/2 m v final squared is exactly equal to F times L, plus 1/2 I omega final squared is equal to F times L. And if that's true, then the translational energy is entirely accounted for by this F times L, which means that the internal rotational energy is unaccounted for. They would have to be 0. And that is not what happens. What I have is another piece of energy here, F times little l. And the little l I haven't shown you on this picture. How would you actually make this F act on the edge of a circle? You would do it by wrapping a thread around the edge of this thing. So what the extended system looks like. The extended system. Here is my initial state. My thread is wrapped around there, and I pull it with a force F. The final state, the disk is here, and the thread has extended a distance L, and I still have a force there. So I've moved a distance capital L, that's the center distance, but my hand has moved a distance L plus little l. So the total work from the surroundings is equal to my force times how far the center of mass moved plus how much the string has unwound. So then I have 1/2 m v final squared plus 1/2 I omega final squared is equal to F times L plus F times capital L. Now I do know from the point particle system that the force times capital L is equal to the translational energy, which means that if I saw how far the string was extended, I could tell you what the internal energy was. So you can use the energy principle in two different ways in every problem You can look at the point system, which tells you how the center of mass is affected by all the forces in the system, or if you can see the details of the system, how far individual forces have acted, what are the individual, you need to know exactly where the pieces of the system are, you can figure out what this internal energy is.